want to go over some problems that we did in class here. This problem is the acceleration between walls. It's the University of Texas problem. Here you have a particle. It's going to travel between two parallel vertical walls. They're located 10 meters apart. It moves toward the opposing wall at a constant rate of 5.8 meters a second. So what that means is the horizontal velocity component of this vector here, of the velocity vector, is going to be 5.8 constant. You have no acceleration along the horizontal. What the problem is asking you to do is what will be the speed when it hits the opposing wall? That's the first question. And the second question is what angle with the wall will the particle strike? Alright, I'm going to show you how to set up this problem. To do this problem, you notice here that delta x, this is going to be your change in displacement along the x direction, is going to be 10 meters. Now we know that from our kinematic equations that we have no acceleration here. So we can just say delta x is going to equal to our velocity in the x direction times our time component. So first thing you can do with this problem is you can find out how long it's going to take to go from here to here. So we just put our numbers in. We put 10 is equal to 5.8 times t. So t would equal to 10 divided by 5.8. I'll grab a calculator. We'll do that real quick. 10 divided by 5.8 gives you 1.72 seconds. So from that we know that the time will equal to 1.72 seconds. Okay, so we know when this particle leaves that it's going to have a velocity that looks like that. Well, we know its y component is going to be like this, and our x component stated here, obviously not going to be this long a component, would go back this way at 5.8. So all we have to do is find this component. Now, since we are going up along this horizontal plane here, horizontal line, that you know when it comes back down, whatever this velocity is, it will be the same velocity when it hits except going the opposite direction. So we can go back to our kinematic equations in the vertical, and we know that the equation V final is equal to VI, I'll make this y minus 9.8 times t. So in this case, we also know that VF is just going to equal to nothing more than VI in the y. Substitute that back in here, then I'll get minus VI times y is equal to VI times y minus 9.8 times t. Move this over, and I'll get minus 2 VI y is equal to negative 9.8 times t, and then VI y would equal to, divided by 2, would give me 4.9 times t. Okay, we know our t was 1.72. That's how long it took to go from here all the way over to here. So now we can take this value here and put it back into our time, and we find out what our initial velocity was at in the beginning. So I get 4.9 times 1.72. That'll give our initial velocity. So get the calculator, we'll run that real quick. 4.9 times 1.72. And that gives us an initial velocity of 8.428. I'll go ahead and put all the values in here. The I and the y is equal to that. Alright, so now let's find out what the actual velocity was here. We'll draw our two components. I have one vector coming up this way. I have one vector coming out this way. This vector here will be the 8.422. This vector here will be our 5.8. Again, we know when we add vectors that we add them from head to tail. All we do is come up here, add that one, and then our resultant vector would be right here. So now to find that value here, and I'll move this up here, it's 5.8 also. Let's go ahead and erase this so it's not hanging out in the air. So then the resultant vector would equal to 5.8 squared plus 8.422 squared. We'll take the square root of that real quick and see what we get. If I square that, plus 5.8 squared, second square root, second answer, that gives me a value of 10.23. So 10.23 meters per second. Okay, now you can ask yourself, if I go up here at 10.23 and I know I'm going to come down at the same vertical velocity except the opposite direction, and I know this velocity doesn't change, then could you not say that this velocity right here has got to be the same thing? So when I hit that wall, this velocity here will also be 10.23. Alright, now I'm looking for this angle here. So this angle here would also be the same as this angle here when I launch, which in this picture right here would be this angle here. So if I'm looking for that angle there, can I not just say that this angle theta, so I can say the tangent of theta is going to be opposite over adjacent. Okay, and then we can take the inverse tangent and say theta is equal to the inverse tangent of 5.8 over 8.422. We will solve for that very quickly. If I take second tan 5.8 divided by 8.422, I will get an angle of 34.55. Alright, and I believe we have everything here. So we have our angle, we have our velocity, and we have our time up here. So we'll see how our solution compares to the real answers. Might be some rounding errors, but we'll be very, very close. The initial velocity here, 10.24. So we're 10.23. We're right there in the ballpark within rounding error. And what angle, what strike? I calculated 34.55, and they got 34.478. Again, it's just how many digits you carry, and that's how you do it. So anyway, that's how you do this problem here. Okay, best of luck on that type of problem.